thought I would put together a video detailing the steps that I go through in processing a basic astrophotography image. The example I'm going to be using is NGC 2237, which is the Rosette Nebula. And I'm going to go through the detailed steps for a luminance image, even though everything I go through I apply similarly to my red, green, and blue filtered images. I'm going to cover data acquisition in a different video. Suffice it to say that I collected a number of light frames in all four colors, and the actual acquisition times depend on the ADU levels I was trying to reach with each individual filter. So those vary from 60 seconds to 180 seconds. The number of frames also vary. I tend to take more luminance frames than RGB frames. For each of the acquired light frames, I also collected flat frames. These are very short. They're only about a second, and they're used to remove dust spots and vignetting that are in the optical train from the light frames. And finally, we need to collect a number of dark frames to subtract out electronic noise and dark current from the sensor. And what I do is I collect dark frames corresponding to the exact same acquisition times as I did for the corresponding light frames and for the flat frames. There's a wide variety of number of frames that you can collect here. I tend to match the light frames and flat frame number that I take, but that's not strictly necessary. Also note, in many cases, people take bias frames. I don't do that since I have a CMOS sensor. Instead, I rely on taking these dark flat frames instead. So in the first step, we're going to start processing our dark frames first, since they're going to be needed for further calibration. So the dark frames and the flat darks are handled in the same way. We're going to use the Pixinsight image integration module to integrate these 120 frames into a single master dark and into a single master dark flat frame. So here we are in Pixinsight. In general, when I go through my steps, I'm going to open up the individual modules in their default configuration so I can show you where I make changes to the module settings. So in this case, the first step we're going to do is go to Process, and under Image Integration, go down to the Image Integration module, and here it is open, and I'm going to just reset it. So first thing we want to do is add our dark frames. And in this example, I'm going to use the dark flats. So I will go into dark flat frames, and using a Mac, so I use Shift and click to select all of the frames, and you can see there are 120 selected. We open them and they populate the path. Our combination technique will be average, since we're averaging all of our all of these dark frames. Normalization, for the darks, we're going to have no normalization, and for weighting, we're going to say all weights are equal to 1, which they laughingly put in as don't care. We're going to make sure that the generate integrated image box is checked, and now we need to pick a technique for pixel rejection. So we'll close this and go to pixel rejection. And the rejection algorithm we're going to use depends on the number of frames that we have. So for this many frames, for a large number of frames, I use linear fit clipping. So we're going to select that. But I'm just going to mention that many people, if you scroll over this rejection algorithm, you can see that there are descriptions about where you would use which rejection algorithm. Many people like to use the Windsorized Sigma clipping. And I use that as well if I have 20 frames, 25 frames or less, but I've had good luck with the linear fit clipping. Once again, we're not going to be doing any normalization. And I also uncheck the map range rejection and clip low range. Instead, I rely completely on clipping of high and low pixels using a set sigma level. So in order to set that level, we close that out and we go to pixel rejection 2. And you can see that linear fit low and linear fit high are highlighted, and these are the sigma rejection levels. I can tell you what I have been using pretty successfully is a linear fit low of 4.5 and a linear fit high of about 3.5 for these frames. And the way I set these is I will show you when they integrate, you can see how many pixels have actually been rejected. And I try to keep that somewhere between 1 and 2%, no more than that. Once we're done, we go down here to the global apply and we hit the button. And Pixinsight is now off to the races. And this is going to take quite a while, so I will get back to you when Pixinsight has finished this job. So now you can see we're done processing, and the computer is opening up a number of frames. So let me close out of image integration. First of all, if we look down here in the process console, you can see under this line that 1.011% of the pixels were rejected in total, and 0.29% were low and 0.72% were high. And total processing time for this step was about 12 minutes of CPU time. So I'm going to close out of this slope window, and what we have here are our rejection maps. So if you go up here to this small icon that has a nuclear symbol, that is our screen stretch function, auto stretch. And we can stretch our frame out and we can see the high rejection. These are the pixels that were rejected on the high side. And if we go down to low, here are the pixels, once again we stretch it, which were rejected for being low. So we will close out to this. And here is the pay dirt for this whole operation. We stretch this. This is our actual integrated dark flat. And you can see it's kind of a boring image, which is great. It shows a little bit of striation from the sensor, but generally it's very, very flat and uniform. One of my other cameras, which is an uncooled camera, has a huge amount of amp glow on this side, and there's absolutely no amp glow on this sensor at all. So what we're going to do is we're going to go up to File, and we're going to say Save As. And we want to make sure we save this as an XISF file for further imaging. And we're going to put it into our Rosette Nebula folder. And we're going to call it a Master Dark Flat. Oops. Flat. And save that. And say OK. And that file is saved for further processing. So in our next step, we're going to focus on generating a calibrated flat frame. So to do that, we're going to use the image calibration module in Pixinsight, use the master dark flat that we just generated, and generate a series of calibrated flat frames. Once these have been calibrated, we can go back and use the same image integration module, albeit with different default settings, to combine all of these calibrated flat frames into a single master flat. So to calibrate our flat frames, we go to Process, Image Calibration, and open up the Image Calibration module. So I'm just going to reset this. First thing we're going to do is add our flat frames. So we go to Add Files, and I already have this open to Flat Luminance Raw, and I'm going to select all of the raw data files. So that's the input, and then for the output, we go to Output Directory and click on the file folder and choose where we would like to place our calibrated files. So I actually have a folder already set up called Flat Luminance Calibrated, so I'll open that up. So we've got our source, we have our destination. Since we are using a monochrome camera, I'm going to uncheck this Enable CFA, which is Color Filter Array. You would use that if you were processing one-shot color samples. Here you see a postfix_C. That means that all of the output file folders are going to carry that _C extension for calibrated. And we are done. We are going to uncheck the master bias since I'm not using bias frames, and we're going to uncheck the master flat. And for master dark, we're going to click on this file folder, and we're going to find the master dark flat that we previously made. Here it is. It's an XISF file, and we open that up. And we want to make sure that optimize and calibrate are not checked. Okay, now we are ready to go, and we hit the global apply button. And once again, it's going to take a while for Pixinsight to process this data. So we just finished the image calibration. You can see 120 frames successfully were calibrated. It took a little over 6 minutes. So I'm going to close out of this and close out of image calibration. And now so just as we did before, we're going to integrate all of these calibrated images. So we go to Process, Image Integration, and open up the Image Integration module. And I'm just going to reset this. So just as we did before, I'm going to add the files, but now I'm going to be adding the flat frames, which have been calibrated. So flat, luminance, calibrated. And we should have 120 of these, which we do. And we open those up. And now we go to image integration. Our combination is average. Normalization, we're going to do multiplicative, and this is done only with the flat frames. And weights, once again, we are not going to weight these at all, so we put down all weights equal 1, generate integrated image. And now similarly to our last rejection algorithm, we're going to use the linear fit clipping because I have 120 files. Normalization here is going to be equalize fluxes. And what this does is it accounts for small variations frame to frame in the flat frame light source. And I'm using a luminance panel to generate my flats. Get rid of map range rejection and uncheck clip below range. Once again, we're going to rely just on the high and low pixels for rejection. Similar to what I had done before, I set this to 4.5 for the linear fit low and 3.5 for the linear fit high. And once we have that, we can hit global apply and we're off to the races. So you may wonder what these magenta warning statements are that keep coming up during processing. These have to do with the PSF signal, point spread function. And that's related to the shape of the stars that are detected. Since we're integrating only flat and dark images, there is no star field, so you wouldn't see a PSF signal. That's why we see the warning. However, the program executes right through it, nothing to worry about, and it'll successfully integrate all of our frames. So the computer is now reaching the end of the integration cycle. You can see it took about 11 minutes to complete this step. And once again, we've rejected about 2% of the pixels from the flat frame. If I'm going to go back, I may increase the sigma sliders a little bit to get that number down. So we will close out of image integration. Once again, get rid of slope. And we can stretch the rejection image high and the rejection image low. And for flat frames and for dark frames, these are not particularly useful. You'll see where we can get some information out of them in looking at light frames. So we'll just get rid of these. And once again, increase the size of our fully integrated image and stretch it. And we can see our flat frame. You can see where it is vignetted in the corner. And these circular areas are dust motes, and you can see some larger ones here, very faint. I don't know if you can see them. But this is dust that is on the front lens and on the sensor itself and on the filters. So since these also exist in our light frames, the flat will both correct for these corner vignettes as well as correct for the dust motes. You can see a little darkness here at the top. This is shadowing from my off-axis guider. So that will also be subtracted out of the image. So we will go to File, and we will go to Save As. And once again, this will be our master flat. So we'll just call it master flat frame. It's an XISF file, and we'll save that. Okay. That is saved, so we are now complete. So up to this point, we've generated a master flat file and a master dark file. And using those, we are finally able to start dealing with our actual light images. And we're going to calibrate them using image calibration and applying the master dark and master flat to correct them and generate a number of calibrated light frames. Once again, we're going to be going back to Process and Image Calibration and open up the Image Calibration module. And let me reset this. So we're finally going to be adding our light frames. So we go back to Light Frames, Luminance, Luminance Raw, and we're going to be selecting all of these 122 frames, and we open them up. Once again, we uncheck the Enable CFA box, and we go down to our output directory. And our output directory for these light frames will be luminance _cal. And we go down, and now we are going to uncheck master bias, but this time we do have a master dark file. We're going to open that up, and here is our master dark. We're going to select that, and we're going to uncheck optimize and calibrate. And this time we will check master flat, and we're going to open up the master flat that we've just generated and make sure that calibrate is unchecked. And now we can hit the global apply button, and I'll be back when this is calibrated. So we just finished calibrating all of our light frames. It took a little bit over 10 minutes, almost 11 minutes. And my poor little CPU cooling fan has been running flat out this entire time. So you can see 122 succeeded, 0 failed. So now it's time to move on to our next processing step. So I wanted to show what we actually accomplished by this calibration step. And here we see one of our raw luminance images. You can see there's a little bit of either a meteor or a satellite trail here in the corner, but you can see that there's vignetting in the corners, and you can see a dark spot here, which is one of the dust motes that's in the optical train. So after applying the calibration, here's the same image, and you can see that in removing some of the electronic background noise, we have a little bit better signal to noise ratio, but most importantly, the vignetting has been completely removed. And this dust mote has also been removed from this area. So this is our first big improvement in the quality of our original light images. Now, you'd think in keeping with our previous workflow, we would now take the calibrated light frames and integrate them. But in reality, there's a bunch of housekeeping tasks that have to be done before we're ready for that step. In the first one, I'm going to use the Cosmetic correction module to remove both hot and cold pixels from the light frames. So these are electronic noise, and we get rid of them for two reasons. First of all, they look awful. They're just additional noise. But beside the cosmetic effect, hot pixels can be detected later on when we try to align our frames as stars. And this is really going to goof up the alignment procedure. So we want to remove them at this stage. To carry out the cosmetic correction, we go back to our Process tab, and underneath it we find Image Calibration, and the very first module is Cosmetic Correction. So we open that up, and I'm going to reset it. And as usual, we're going to add the files to be processed, and I am looking at my luminance calibrated files. So these are the light frames that we just calibrated, so we'll select them all. 122, And we're going to select a destination directory, output directory, click the file folder. I'm going to put them in a folder I've already set up called cal_cc for cosmetic correction. And we open that. Once again, we make sure that the CFA box is not checked. And you can see that the files that are outputted will now have a _cc postfix to identify them. And we have a couple of choices now of different ways we're going to detect these hot pixels. I use the auto detect function. So we click on that window and we click on hot sigma and on cold sigma, and right next to it are some sliders. They're set right now to 3 sigma, but we're going to have to figure out how to set them. So we'll go into that in a second. I also open up this real-time preview window, and what this does is it gives us a scoring of how many pixels in a field of view are going to be removed. So you have some idea if we're taking away too many or too few. So to set the signal levels, we're going to go and find a file. It could be any of the light files, and just double click on that file. And we'll see the image open. I'm going to just blow it up. And once again, use the screen transfer function to stretch the image. And here you see finally our first view of our light frames. And you can see the nebulosity from the Rosette Nebula, and in here we have either a meteor or some sort of a satellite trail that we'll deal with later. But typically what I would do is I would zoom into this and look around to try to find an area where we have some hot pixels. And I've done this previously, so I can actually go out and use this icon up here, which is our preview mode. We click on that, and now we can generate a blown up preview of any region we'd like. And the area that I had found some earlier hot pixels was in this region here. So we're just going to generate a preview. And we're going to open up that preview window, and I'm going to expand it. And sure enough, here you see a glaring hot pixel right in this area. So in order to figure out our sigma level, we're going to first of all hit this open circle, which is a real-time preview. And we see the same image. And the pixel is gone. It's been removed by the cosmetic correction using this sigma level. So just to demonstrate, if I slide the sigma level to the right, which makes it get larger and larger, at some point you can see that pixel comes back. And if we move it to the left, you can see that we can add or remove that pixel. And down under the real-time preview, you can see the score changing as we remove that pixel level. So what happens if we get too far to the left? We choose too low of a sigma number. You can see we start removing random noise, and we wind up with a really ugly, plasticky looking image. So we don't want to be too low. So it looks as if the 3 sigma level that we started with was actually a pretty good place to start. I don't worry too much about cold pixels because with modern sensors, there's very few of those anyway. So now let's see what happens if we would apply this to the full image. We close out of the preview, and what I do is I delete this preview window. So we've got our full image. And once again, I go here to the open circle and I generate a preview window. And what it's going to do is apply our current sigma settings. And you can see in our full image, we're going to remove 1,322 hot pixels and a little under 1,000 cold pixels, which, considering that this is a huge file, that is very, very little. So that seems to be acceptable. So we will close out of the preview window. And now we take the corner triangle and we drag it onto our actual image. Oh, actually, it can't be done with cosmetic correction. We're going to have to do the global apply button, use the global apply button as we have in our other modules. And you can see it's running through the cosmetic correction, and we'll go back once it's finished. So we just finished the cosmetic correction step. 122 succeeded, You can see it took about 8 minutes to complete this step. So now it's time to start to sort through our light images and see which ones will go forward into image integration. So our next step is actually fairly non-technical. We're simply going to look at all of our frames and get rid of those that just look abhorrently awful. So to do that, we're going to use a blink module, which is a great way to scroll through many frames very quickly. And we're going to basically take our cosmetically corrected light frames from their folder and reject the ones that are really awful into a junk folder. So that way we're not actually deleting any files at this point in case we want to change our mind later. So let's go and take a look at how Blink actually works. So to use Blink, we go to our Process tab, and it's a little bit different than our earlier modules. It doesn't actually exist under any of these subheadings. So we have to go to All Processes, and that's where we will find Blink. So we execute it, and this window opens. So now we can load our files using this file folder, and we're going to go to our luminance_cc, cosmetically corrected files, since these are in the latest stage of processing, and we're going to open those. And we're just going to wait to have Blink load all of these file folders. So we're at the end, and Blink is finished loading all of our files. And now that they're loaded, you can see that a window is opened and a screen stretch is applied to our image. So what Blink actually does is sequentially goes through these files in the order that they're put in the file folder, much as you would a movie. And you can see we've set a frame rate of 0.05 seconds between frames. If we use this run command, you can see we've got a rudimentary movie of all of our images. So you can see here is where I tracked into the trees behind the leaves. Then at about this time, the clouds came out. Now we've got a lot of high clouds that are obscuring our view. And once again, we start over at the beginning. So if I stop this film, I now know I have some issues at the beginning and at the end of all of my frames. So let's starting at the first, I can now scroll down with my down arrow until I get to the first completely clean frame, which is this. I now choose the one before that, which is my last problem frame, and I can go to the top here and select all of these frames. And if I click on the check mark, you can see they're all unchecked. What unchecking does is it signals Blink to ignore those frames in subsequent runs of all of the images, so it just skips over them. So let me go and run forward, and we're going to run down to the point where we're once again just going into the trees right there, and I'm going to scroll up to the last known good frame, and I'm going to do the exact same thing, but now get rid of all of the frames at the back of the image. So we're going to uncheck those. And now when we run, we should see only those images that we want to keep for subsequent integration. And there it's run through them. And it looks pretty good. You notice that there are some fluctuations in brightness. There's also some satellite and meteor trails, but all of these can be removed later on in the integration step. So this is a pretty good data set. So what I'm going to do now is remove the problem files from the cosmetic correction folder. So to do that, I go to these unchecked boxes. I'm going to select these top ones first. And down here, we have this symbol file with an arrow. If we click on that, it's going to cut the files from the cosmetic correction folder and put them somewhere else. So I'm going to find a destination for them. And in Rosette Nebula, I do have a folder which I call junk. And I'm going to say open. And what it's doing now is transferring all of those folders into the junk folder. And we go down. I'm going to do the same thing with all of these files toward the end that I just rejected. Starting here, going to the end. And once again, move these to a new location. And once again, they're going to go to junk. And we say open. Okay, so now if we clear out all of the folders here in Blink, we're going to close all the images and now go to reopen them. If we go and do what we did at the beginning, which is go into our cosmetic correction folder, now we're going to see rather than 120 files, we've only got 40 left. So these are the ones that were accepted. And once again, we can open all of those up in Blink and run through them. And if we run the Blink module, you can see just these are only the best of the file folders that we have for imaging. So we are done with this, and it's time to move on to subframe selection. With the remaining files, we're going to take them through one more filtration step using a module called the subframe selector, and it will do two different things. The first thing it does is it scores all of the images based on a number of different criteria. For instance, it'll look at the star shapes and see if they're elongated. It'll look at the number of stars in the field to see whether or not there were clouds obscuring the image. And then we can set certain rejection levels within the subframe selector. If the frames are rejected, they're moved into that same junk folder that we use to reject frames using Blink. The second thing it does is it weights each of the frames depending on its quality criteria and uses those weighting factors later on to apply them more or less during the image integration step. So we're going to reject frames, we're going to weight frames, and then those frames, along with their weighting functions, will be put into a folder called the Approved Light Frames folder, and we're ready to start prepping those frames for integration. So the use of the subframe selector is a little bit involved. To open it, we go to Process, Image Inspection, and open up the subframe selector module. And three windows will open up: a measurements window, an expressions window, and the main window here. So looking first at the main window, we want to make sure that we are in measure subframes. And then we're going to add the files we're going to analyze. So the files are the luminance _cal_cc for cosmetic correction, and we'll choose all of those. And we open those up. And now we have to put in a couple of system parameters to describe our optical system. So the first thing we need is the subframe scale, and we can get that actually from any one of these images. If we just double click on it, I'm going to just minimize these windows. So we've opened up our image, and to see what it is, we can just stretch it with the auto stretch. And there is the Rosette Nebula. So what we'd like to do is plate solve this image to get an idea of what the resolution is. So we can do that by going up to Script and down to Image Analysis and down to the Image Solver. So this plate solver will open, and the first thing we need to do is put in the parameter for the coordinates for the Rosette Nebula. So we can search, and we just type in Rosette Nebula, press the search button, and there it is. We just opened up, and there's a number of choices. We'll just take the very first one, Rosette Nebula, and say OK, and the coordinates are loaded in here. Our focal distance is about 655 millimeters, and my ASI 6200 mm camera is 3.76 micron pixel size. So now we can say OK, and the computer will try to plate solve the image. This takes a couple of seconds. And the image is solved. And here under resolution, we can see 1.142 arc seconds per pixel. So we will put that in here, 1.142. And that's the first number we need. The second one we can get still from this open image. Now we go up to File and we say open up the fits header. And this has all of the acquisition parameters associated with the image. Under eGain, we can see 0.77999 electronic gain in electrons per ADU. So 0.77, actually 0.780 would work. So we will put that here under camera gain, 0.780. And now we can close out the fits header and close out our image. And we can maximize our subframe selector measurement window again. So the next thing we have to put in is the camera resolution, which is 16-bit for the ASI 6200mm. And the site local midnight was 5 hours before UTC or after UTC. So we just put in 5 hours there and we are done. Now we need the output directory. So if I click the file folder, I'm going to put the output files in luminance cal _app for approved. And then the only other thing we need is a keyword. And this is the keyword that's going to be used to associate the weight for each one of the frames that's been assigned. So once we are done, we can hit the global apply button and the subframe selector starts working. So subframe selector is done, and over here we see a graph of the subframes in order that they appear in the file. And in this case, the PSF signal weight is the parameter we're measuring. So let's go and look at the full width half maximum, which is an indication of the focus. And we can see that a couple of our frames are kind of high. We'd like to have this number ideally below 5. And we can look at the eccentricity, and we can see that we have a couple of frames here that also have very high eccentricity of the stars. So rather than go parameter by parameter, we can go down here and put in an expression to assign weights. And here's the expression that I'm using. It looks at 3 factors: the full width half maximum, which is an indication of how well a star is in focus. Then there's the eccentricity, which is an indication of how well we're tracking the star. And then finally, the stars count. And the reason we use the stars count is in case of a cloud passing over, sometimes we can actually get a very favorable eccentricity or full width half max number, but it's because the star is largely obscured by clouds. So we want to keep a high stars count. Once we have all these parameters in place, we can hit this triangle, and these weighting factors are applied to our images, and they show up here as a dotted line. So the dotted line shows the weight. So if we go here to the weighting function, we can see that of all of these, we have one extremely low weighted frame. So if we go to the top, we can sort by weight. And when we do, here's the very first one. You can see the weight is substantially lower than the others. So we can double click on this file name and open up the image. So I'm just going to minimize right now that window, and we're going to stretch this image. And it looks pretty fine until we start zooming in. And you can see the problem here. Every star is doubled. So somewhere in the point of acquisition, either the wind blew and the telescope shifted, or maybe I bumped into it, but we're seeing a double image, which is why this is receiving such a low score. So we can close out of this image. And if we open this, we can either set a criteria here for approval, or we can just click on that image like so. And you can see here a little X appears, and it's been locked and selected for rejection. So let's take a look at some of our other parameters. If we take a look at full width half maximum, you can see that that star was also very high, which made it unfavorable. And if we take a look at eccentricity, it was also one of the highest. Wouldn't have been rejected for that reason alone, but in combination, that is a bad frame. So if we go back to our weights, we'll look at some of the other factors. And you can see that there is one star set here that actually has a very high weight. And we're going to go down and look at that. That is frame number 1642. So we're going to remember that as one of our better frames for selection. So now that we have looked at our parameters and we have decided to reject this one, we can actually go back to the measure subframes and reject this automatically. So we will go to output subframes. And now when we hit this, we will assign weights to each of the files and pull that one rejected frame out. So only the remaining files will go into the approval folder. So once again, this will take a little bit of time. And there we go. 39 succeeded, 1 failed, and 1 was skipped. Took about 13 seconds to do that. And we are done with the subframe selector. So we can close out of this. So now if we go to open, our files, now we're going to go into our Rosette Nebula, and we're going to go into light frames, luminance, and the approved folder. You can see at this stage, we've populated only with the approved images from the subframe selector. And we are down now to only 39 from 40. So from our starting 122 frames, we're literally down to only 39 good ones at this point. So we're nearing the end of our journey, and we're almost ready to integrate our frames. But before we do, we have to star align them, or in other words, register them so that they line up for integration. So we do that with the star alignment module in Pixinsight. And this does two things. First of all, it lines up all of the frames and stacks them so that they are ready for integration. And it also opens up a drizzle data file. That file is not yet populated, but it will associate a drizzle data file with each of the registered light frames. Now what drizzling is a digital image processing technique. And it was developed actually for the Hubble Space Telescope. But it does a linear reconstruction of the image. And it's really, really great for undersampled images. I use it regularly, even though my samples are not grossly undersampled. The downside of it is that it can literally double the size of your files. So if you've got a lot of storage space, it's not a big deal. If not, you may want to use this warily. So let's continue on and do our star alignment. So to align our frames, we first go to Process, and under Image Registration, we will find the star alignment module. So we click on that to open it. And first thing we're going to do is pick a reference image. And if you remember before, we identified a good quality image during the subframe selecting process. So we're going to go here to File and click on this triangle. And now if we go into our approved folder, that particular frame was 1649, which is here. So we'll open that up as our reference image. And what we would want to do if we were doing all four colors, L, R, G, and B, is pick one throughout all four colors, 4 channels, and have all of the images line up on that one star field. So now we're going to make sure that local or generate drizzle data is checked, and we're going to add our target images. So we say add files, and we go back to our approved folder, and we're going to select all the approved frames. We've opened and they are added. Our output directory, we click on the file folder again. And if we go to our Rosette Nebula, into light frames, luminance, I have a file here which is underscore normal, norm, and drizzle. And what we're going to do is use this folder for these registered files, and then we'll also put our normalization and drizzle files in the same folder. You'll see that in the next step. So we say open, and at this point we shouldn't have to touch anything. We hit the global apply, and we wait for Pixinsight to complete the process. So star alignment is done. It took a little bit more than 2 minutes to complete, and you can see 39 files were successfully registered. So finally, we're at the last step before integration, and this is the use of the local normalization module to generate normalization data from our registered light frames. Each of our light frames has a slightly different brightness level, and what normalization does is it tries to assign a weighting factor to each based on the relative brightness of the frames. And once we have that data in hand, we can finally integrate our registered light frames. Normalization, I'm going to go to the Process tab and down to Image Calibration and open up the local normalization module and reset that. So the first thing we're going to do is choose our reference image, and we'll use the same one that we had used before for registration. We'll say File, Open, but now we're going to go to our file folder containing all of our registered images. And 1649, which is here, is the image that we had chosen as a reference. And now we're going to add our registered files. So we go to the registered folder and we pick all of the registered files. Note that there's also drizzle files in here. They're not populated yet. They've just been set up in our previous step. So we say open and they've been added. And for our output, we're going to pick a file folder, and we're actually going to go directly into the registration file. So in the registration file folder, we're going to wind up with our image files, the drizzle files, and then the normalization files as well. So we open that folder and we're ready to go. So we hit global apply and we will let Pixinsight process this data. So local normalization has been completed. It took a little bit over 10 minutes, but all the files are ready to go to our final step. So in the final step, we will now take our registered light frames and use image integration along with the normalization data to generate a master light frame. And at the same time, image integration is going to populate the drizzle files that we generated earlier with drizzle data. And I'll show you in a second what we'll be able to do with that. So we finally come to the point where we can integrate our light frames. So I'm going to go to the Process tab and down to Image Integration and open up the Image Integration module and just reset it. So first step is to add our files, and we'll say Add Files. And now we go to the Registered Images folder and add our data files, which are the XISF extensions. And we'll just select all of them. Next, we'll add the normalization files. And we go to that exact same file folder, but these have the XNML file extensions. And we'll add all of those. And finally, we're going to add drizzle files. And these are XDRZ extensions. And all of these are in that same registered file folder. So we choose those, open them up, and all of our data files are ready. We're going to go to combination average, and our normalization will be local normalization. Our weights will be the fits keyword. And this is the word that we generated earlier during the subframe selection process, and that was SS weight. And we're done with that. So now we're going to go down to the pixel rejection, and we are going to use our linear fit clipping. I believe so. Let's see how many files we have. Yeah, we have a total of 39 files. So I'm going to use the linear fit clipping. Normalization is local normalization. And once again, I'm going to get rid of the map range rejection and uncheck the clip below range. And finally, we're going to go to our pixel rejection. And once again, set our linear fit low to about 4.5 and our linear fit high to about 3.5. So once this is complete, we're going to hit global apply and let the computer do its thing. So we finally completed the integration, and you can see 39 drizzle files have been updated. If we go up to the end of our integration, you can see that just about 1% of our pixels were rejected. That's 0.76% of the high light pixels. So we're going to close this out and close out the image integration. And I usually don't do anything with the slope, so we'll get rid of that. So here is our high rejection frame, and if we stretch that, we can see that we've rejected a number of pixels in the field, but more importantly, a couple of satellite trails which have been removed from the images. So this rejection level seems to have been set properly, so we can get rid of that. And if we stretch our low pixel rejection, we see just a bunch of general noise, not many pixels removed at all. So we can close that, and here is our final integrated image. We'll stretch that, and you can see we have much nicer signal to noise than we did in our original image. The nebulosity is very clear. We see a lot of the dark channels in the nebula. There's some problem here with, I think, our secondary reflections, but I can try to crop those out later. So we're going to save this image. We'll say File, Save As. Once again, this is going to be an XISF file, and we're going to call this Rosette Nebula Integrated, and we'll just save that. That's been saved. So now we are ready for our very last step in this process. But before we move on, I'd like to show you what we've accomplished by all of these processing steps. Here on the left is a single calibrated light frame that we generated of the Rosette Nebula. And on the right is the integrated light frame, which is the result of all of our processing. You can see the increased signal to noise ratio of the Rosette Nebula itself. You can see how we've taken care of the vignetting in the corners of the image and generally smoothing the background. And finally, you can see here on the left where we have some satellite trails. They've been effectively removed from the image. Also here, where we've got a region that's dark as a result of some dust motes, that's also been effectively removed in the integrated light frame image. So now we can finally get on to our final generation of the drizzle data files. So in generating the master light frame, we've also generated and populated our drizzle data file. So we can finally use the drizzle integration module, which will utilize that drizzle data as well as the normalization data to generate a drizzled master light frame. And at that point, we're at the end of our pre-processing steps. Carry out the drizzle integration, we go back to the process menu and down to image integration and open up the drizzle integration module. I'm going to just reset this. And now we will add files. And the files we're going to add are the registered image files that are in our luminance registration folder. So we will now select all of them. And we're going to add the local normalization files that are found in that exact same folder. And there's nothing else to change on the defaults. We're using a scale factor of 2, so we hit global apply. And this is going to take quite a bit of time now to process all of these images, so we will get back to it in a second. So after 19 minutes, I've reached the end of the drizzle integration step. 39 of our images were successfully integrated. So I'm going to close out of this module, and we'll apply a screen stretch to the final drizzle integrated image. And it's really nice. It looks a lot like our integrated image, and I'll show you in a second how it differs. There's a couple of reflections up here that I'm going to wind up cropping out in my final processed image. So what I would typically do now, this completes the luminance image. I would go back and go through all of these steps for the red, the green, and the blue. Or if I were doing narrow band, I would do the same thing to the hydrogen alpha, oxygen 3, and sulfur 2 images. So it's a lot of work, but at the end we would have a single image for each of those color channels. And then we could continue on to do some additional processing steps. So here I've looked at 5 stars in this very zoomed in frame from our integrated image, and looking at this exact same field of view using the drizzled image, you can see that the pixelation is much less pronounced. And this is why this is such a great tool to improve seriously undersampled images. Now, the downside of this, beside the processing time, is you can see that the file size has gone from 240 megabytes all the way up to almost a full gigabyte. So this is something that you can do if you've got a lot of hard drive storage space, but just be wary that it does eat up a lot of storage. So this ends the video, and I hope you found it somewhat useful. This is by no means the only way or even the best way to process the images, but it's the way that I use right now. So thanks a lot for watching, and clear skies.